Hey, how's it going? Thanks for joining me for part 2 of the Vectorization with Python study session. It's later in the day, so I'm a little bit tired, but I wanted to get back on here and just, keep going at it because I got to get through this. We have to get through this. You're my pair programming partner, and we're going to get through this together. So let's just go ahead and pick up where we left off in the last video. We were looking at just playing around with vectorization using the Numpy library. The last thing we did here is we were looking at how using vectors of different sizes is going to throw an error when we try to do things with it, like adding vectors together and multiplying or whatever. It's going to require us to have vectors that are the same size in order for those things to work. Now, one thing I wanted to fix from earlier is I was doing these like single vector operations, and I put division and multiplication in here prematurely. What I did there was not wrong. I just want to put them in their own like separate category down here. So what I'm gonna do is I'm just gonna paste them down here, and I'm gonna call this category vector scaling. I'm gonna call this scalar vector operations, because what's happening here is I'm actually scaling in the positive and the negative sense, and it's similar to what's happening with these single vector operations, but I think it's worth it to have them in their own category. So I'm just going to move that down here real quick. I just want to make my notes as easy and organized as possible because I do tend to use these. What I do when I take notes and stuff is I'll either save them on my computer, like in a notepad, or here in Jupyter. But another thing you can do as well, especially if you're going to be working professionally and you want to have access to your notes and stuff, is just put your notes in GitHub, so that you can always use them. And I did that for a very long time with my student notes and stuff. So I'm probably going to end up putting these on GitHub, one to share, but also for myself, So vectors can be scaled by scalar values. So scalar value in this sense would be like this 2 here. So we're taking a vector and then we're scaling it. Oops. We're using this operator, this multiplication operator, and we're scaling it by 2, which means that for the entire vector here, all of the elements are going to be scaled by a multiple of 2. So and I can actually bring down this here so we can see what our original vector was. So our original vector is 1, 2, 3, 4, and we're scaling it by a multiple of 2 here, so it's 2, 4, 6, 8, and then we're scaling it by 1 over, or we're dividing it essentially, so scaling it like in the, what's the opposite of scale? Reducing it, maybe? I don't know if that's the right term, but it's like division, basically. It's just division, okay? It's not crazy, don't worry. But yes, it's essentially the same thing. And I want to just test here, does this scalar vector operation, I'm assuming it'll work with addition and subtraction. I did see that it worked with modulo, but I'm leaving them, I could actually, no, modulo wouldn't make sense here. Modulo might make sense for me to bring up here. I'm just gonna do the modulo one up here real quick. For all elements in A. So the modulo of all elements of A, I know that works because I did that in the last video. Cool. I'm gonna fix the spacing on that real quick. Okay. Oh, my cat is active and the amber lamps are outside. This is getting real ghetto over here. Clue, what you doing? Y'all want to see my cat real quick? Here, y'all can see my cat. She's a little cutie. Look at her face. Okay, girl, don't scratch me, please. Don't scratch me, please. Not in front of the people. Okay. So if you hear crashing noises and running around, just mind your business, cause my cat is having fun. Okay. Just relax. Just chill. Okay. Okay. So yes. The modulo worked up there, and I'm gonna try this here with this scalar vector operation with addition. So add to all elements of A. We'll just call it A. So I'm gonna try that. And see if that works. Okay, that worked like I thought it would. So, yeah, I'm gonna just check for typos real quick. I feel like I missed something. No, that worked. Okay, okay. Cool. And then I'm just gonna do the same thing for subtraction. Right, quick. Hopefully my cat doesn't start meowing like crazy. I feel like she is. If I give her any amount of attention, she just wants more, and then it becomes this whole like, you know what I'm saying, like. It's never enough. Then I gotta get the snacks. Then I gotta get the scritchy scratches. Then, you know, more water, more snacks, more scritchy scratches is an endless cycle. Just save me. All I wanna do is code, baby. Please. Meow, meow. Meow, meow. 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 I wish I could see the way she's looking at me. There's a look of desperation in her eyes. Okay, so let's get back to this. I love my cat, by the way. Okay, so these are scalar vector operations here. Cool, and I don't think the spacing matters, but I'm just gonna see real quick. Okay, yeah, spacing doesn't matter. Just got to double check because, you know, sometimes languages are crazy. Okay, so next thing we're going to do is we're going to look at the vector dot product, and this is going to be pretty important for our multiple linear regression. I'm going to explain that here in just a second. Let me just get this title up. Vector. Whenever you see vector in my notes, just mean that that's like concerning something that's occurring between two different vectors. When I first read that, I was like, vector, what does that mean? Okay, so like I said, this is a pretty important thing. This is significant for linear algebra. And it is also a pretty staple part of the Numpy library. It's like Numpy library makes a lot of this possible, because if not, you would have to do this manually. And so here in the notes here, if you go check out the notes on vectorization that I put in the comments in the notes down below, open up the PDF that is on my LinkedIn. And you go to that and you'll see that I have some comments, my notes have some comments here about vectorization versus non-vectorization. And the example that I give you here is how we're doing the vector dot product in a vectorized way versus doing it in a non-vectorized way. And you can see here how the non-vectorized way is very lengthy amount of code comparatively. And also this is lower performance. And so basically what we're doing here with this dot product multiplication is we're taking two different arrays and we're multiplying each of the indexes of those arrays by each other, and we're creating a new array that has the same length as both the original arrays, but its elements are the product of each of the elements multiplied by each other. Hopefully that makes sense. I actually can put an image in here. Let me go ahead and grab this image, which may help. One second. I'm gonna change this music for a little bit. I was getting a weird clicking noise, like a turn signal sounding like there for a second. Okay, so I'm gonna put this image in here. It's not gonna work. I need to actually get the image first, right quick. There it is. Images. And what is this called again? C1W2 Lab 4. Okay, here it is. And I think I can just drag and drop this. Yeah. So, did that not work? Let me copy the path, or relative path, I think is what I need. Why is this not working? There you go. And that is really large. I'm gonna make this smaller. Okay, so this is what I was explaining here a second ago with the dot product. What's happening, oh, that's too large. What's happening in dot products, we're taking two vectors and we're saying, like, for vector A and vector B, we're going to look at each index of each of them and we're going to multiply the pairs, the indexed pairs between the two arrays, and then we're going to create a new array that has all of the pairs that are the products of each pair added together. So this is really a summation, essentially, but this is a summation that is specific to multiple linear regression. And it'll make more sense when I get to that video, but this is an essential thing that really is supposed to be able to happen in order for our machine learning stuff to work with more than one variable. By the way, multivariate and multiple linear regression are not the same thing. I haven't looked into multivariate, I just know that it's a different thing, so don't get the terms mixed up. That's what they say. Okay, so the dot product multiplies the values in two vectors. The dot product multiplies the vectors, or the values, in two vectors element wise, and then sums the result. So this is a summation, and in math notation it is sigma, or just sum, I think we can do. Oops, I got the wrong symbol. These should be dollar signs. My bad. Oh, you know what? It's not going to work. I don't think it's going to work unless I have. I think I can just do sigma like that. Maybe I have to do capital Yeah, it's this summation symbol right here. So when you see that, which is this here, that's summation, and the summation is, it'll be summation, and then it'll have a limit. Actually, I can just copy my formula right here. So it's limits underscore, and then it'll be man, I'll say one thing I hate about living in the city is the noise. Y'all, it's real. I'm just going to copy this and then modify it. It'll be easier. Okay, so I think I did that's redundancy there. Okay, so we're gonna change this from being 1 to we're gonna change this n to be n minus 1 because this is 0 index, so we need the lower limit to be 0, and we want the upper limit. I'm sorry, we need the upper limit to be n minus 1, and then we need the lower limit to be 0. In this case, it's going to be I. This is just an example, and let's make this A and B, and A of I and B of I. Is that right? And then before this we have A C dot B equals, did I do that wrong? What is it? C dot. Okay. Let me put this on its own line as well, I guess, to make it cute. You know, the code's gotta be cute. We don't like not cute notes. Cute, organized, fun and friendly, and all that. Okay, so what's happening here is basically this right here. I just wasted my time apparently, did it myself. But this formula right here, this is a mathematical notation that explains what this dot product is doing. So summation means that the results of this operation for the entirety of the range from this max to this min, from this min to this max, it's all going to be added together. So A times B for each index will be added together. And that's what we're going to be doing, because with the multiple variable linear regression, it'll be like weight times bias for each of the weights, or for each of the, it'll be weight times the input for each of the inputs. And then all of that is going to be added to the bias. But there has to be a way that we can do that for each of the weights and the inputs together in an easy way. And this vector dot product is how we're going to do that. So that'll make more sense when we get to it. So for this, we're going to utilize a loop, and it's going to, let's see, I'll just type it out here instead of saying it. So we'll be implementing function which returns the dot product of two vectors The function returns given inputs A and B. Now, you don't need to do like a whole function for this. You don't need to do a whole function for this because there is a method that will do this for you. I'm trying to think, do I want to actually I'm just going to copy what I have here. This is the actual function. So if we were doing this manually, this would be the non-vectorized way to do this dot product, like this. I already have it here in my notes here, so I'm just going to copy and paste it instead of doing it again. I'm going to just make sure I put a comment here, non-vector approach. Change this to Python. What's basically going on here is, I'll just explain here what's kind of going on. But first, let me put this in a function. Okay. Oh, excuse me. Actually, I'm just gonna go ahead and copy theirs. It'll be easy. I already did this for myself. Usually I don't like to copy and paste stuff from tutorials, but in this case I'm just gonna do it because I already did it over here and I already understand what's going on. So I don't feel like anything is being lost here. I will do the actual Numpy method one manually though. But for this I'm just gonna, because this is not the way that I would do it, or you would want to do it anyways. So this non-vectorized approach, this is essentially based on this summation formula, like the more literal way of doing this, like straight up. If you were doing this without any type of, package or anything to help you, it would basically be this. I don't think I have anywhere I could put this. I'm just gonna leave it out. Okay, I'm gonna leave it out. That's fine. So this would be the non-vectorized approach, and then now we can do this vectorized approach using NumPy. So A equals, we're just going to create some vectors here. I think this stream is only going to be 1 hour long, by the way. Just because it's like super late. Well, it's not super late, but it feels late. It's like 9 o'clock. Yeah, it's past my bedtime. It's a startup week here in my city, so I'm excited because I'll be able to go to an event tomorrow and do some actual socializing with people in the tech community. I mean, in real life, I haven't been out and about in the tech community in quite a while, so I want to get some good sleep for that. Okay, it's not broken. Okay, so next we want to print. We're just going to print out we're going to print out what this C evaluates out to, and what we're expecting is to do this operation here. Basically the same thing as was done here, but it's going to be faster and it'll do vectorization. It's not super apparent why this is more efficient, why this vectorized approach is more efficient because of the scale of this. But like with scaling to larger data sets and larger vectors, then it'll be more apparent. So you'll have to kind of take it on faith and documentation at this point. My cat is having a good old time in the background. C comma np dot a comma b, and this is going to maintain the shape of the original vectors that are being used in this. So these are going to be 0 or 1-dimensional arrays. So this will return like nothing basically, or it'll be like an empty parentheses. So we're expecting when we get C dot shape. I'm assuming that we can do this with multiple dimensions or dimensions beyond 1 dimension. And we can test that theory out as well. I'm going to do this backwards. It's backwards 2 here. These results should be the same, by the way, between these two. And they are. Perfect. Okay. So, really quick. I want to just try something. I'm going to put this inside of inside of square brackets, and I'm going to make another array here, and I'm going to do 2, 4, 6, 8. I just want to see what happens if I do two-dimensional arrays, just to see. I'm going to change these numbers. I'm going to do like this. Oh, I wonder if these can't be like that. So this is what happens when you start doing stuff outside of the examples. You start finding things to get lost in. Let's see. I don't know if this is even valid, to be honest. For 2D, so I'm just going to Google here, or DuckDuckGo rather, np.dot for 2D arrays. It says here that you're supposed to be able to do this. For 2D arrays, it is the matrix product. That's what it says here. P dot dot. Now what am I doing that's not right then? It says shapes not aligned. I'm just gonna Google this. Value error, shapes not aligned. Watch it be something obvious. MP array. Okay. MP dot dot. I'm just gonna copy this and do the same 2D vector in both of these. Okay, just making sure there's nothing I was doing weird there. I'm a little baffled, baffled. Do these need to be in brackets? No? Oh man. Shapes 2, 4 and 2, 4 not aligned. 4 dim 1. What is dim 1? Oh, excuse me. 4 dimension 1 is not equal to 2. For dimension 1, if the last dimension of A is not the same size as the second to last, Now, why did that work? I am so confused right now. I'm so freaking confused right now. Why didn't that work? Why? Somebody please explain to me. Somebody please explain to me. Why did that not work? I'm so confused. It's too late. My brain is not going to be able to process this right now. I'm just going to enter this in and see if anybody has had this exact verbiage of problem. Something about reshaping. What is reshaping? What does that mean? Gives a new shape to an array without changing its data. The new shape should be compatible with the original shape. If the let me get rid of this, or actually let me just go ahead and comment this out. I'm gonna call I'm gonna print the shapes of these just to see what's happening here as a debugging thing. This is, I'm so far off from like the actual thing I'm supposed to be doing, but this is fine. I'm learning something here. The shape of A A dot shape, and then I'm going to do the same thing for B as well. These are the same shape. What are you talking about? What are you talking about? You know, I don't know why this isn't working. So I have two choices right now. One choice is I could just keep moving forward because this is not essential for the actual thing I'm trying to accomplish at this exact moment. Or my other choice is I could just sit here and bang my head against the wall. I guess there's a third choice, and I could try to figure out like why this doesn't work later on, and I can leave a note for myself, which is what I think I'm going to do. So what I'm going to do is I'm just going to come down here, and I'm going to leave a note and say, why doesn't this work? And I'm going to put it down here. I'll bring this here. And then I can just do this later on so I don't have to get blocked right now. This is what I would probably do in an actual like job situation, because getting blocked is not a good look. So and I'm going to restore this. Okay. So we can move forward for now, but yeah, I am a little bit just concerned why I wasn't able to get this to work. I'm sure you're probably looking at this like, well, duh, you can't do that. But I want to just know why this doesn't work. And probably when I have more rest behind my eyes, I'll be able to do that. Looks like here, what we can do is we can analyze the speed of these two approaches, the loop version of this versus using the Numpy dot product method. And I'm gonna do that, and then I'm gonna get off of here for now. So yeah, this will probably just take me like probably 15-ish minutes. Depends on how many tangents I go on, but yeah, we're gonna keep this to this last thing here. Let's see. Oh, excuse me. So tired. I wonder if I yawn in real life. Do you also yawn on your side of the world? Okay, so measuring the efficiency between vectorization and looping. I'm gonna sleep very good tonight. Okay, so random seed 1. I'm gonna make a very, very large array because this efficiency measurement, it's more meaningful with larger data. I'm kind of scared to print this, but at the same time, I want to know what this actually looks like. Let me save this first, just in case. Oh, these are just really large numbers. Oh, I see what it did here. It doesn't print all of them. It just kind of gives you an example. Okay. What happens if I like pull the index of like 5,000? Does it actually give some? Okay, so yeah, this is up to, wow, what is that, 10 million? I'm gonna try 999,000 index. Okay, damn. Okay, so yeah, these are very large arrays. I don't know what this seed does. I've seen people use the term seed in different things, but I'm not sure what a seed is. Let's do some purple color. Okay. Oh, I think this is gonna be a big topic. This might be too big for tonight. Okay, so in order for Numpy to generate a pseudo-random number, you have to provide a initial input. And that, I guess, is like what the algorithm uses, and different seeds are going to give you a different generation or something. I don't know. That's too big of a topic for right now. Okay, I'm just gonna have to take it on faith and documentation at this point. Faith and documentation. I feel like I need a shirt for that. Okay, so we're gonna capture the start time and we're gonna capture the end time. The way we're gonna do that is by doing time.time. Just gonna basically create time from whenever this is executed. Forgot the E here. And then we're going to do the dot operation for A and B. And then talk. TikTok. And this is going to be the end time. And then we're going to print this dot product, and we're going to format it as a float, and we're going to provide some we're going to do a float, and we're going to have it to the one, we're going to have it we're going to have a decimal and then 4 numbers at the end. Was that the thousandths place or whatever? For F. Just going to print that real quick just to make sure it works. Okay, so yes, that is the processing time that it takes for it to perform this here. And that's pretty fast. But we want to get an actual number here. So to get the actual number here, that's pretty fast for as many numbers, because remember, this is like, what is this, 10 million? Yeah, it did that in a blink of an eye. Probably faster than the blink of an eye. So we're going to multiply our end time minus start time. And then we're going to format that to 4 places after the decimal. And that's going to be milliseconds is what that's going to give us. So yeah, that took like 3.72329 milliseconds. That's really fast. It's very, very, very fast. It's very fast. Okay. So we can do the same thing. I'm just going to copy this a little bit here. Except we're going to change it to use my dot instead of np dot. And then it's going to give us what I assume to be a longer amount of time for this to run. Yeah, you see this is still running here. Yeah, that took way longer. That took way longer. Now, one thing to know is like this is still sitting in memory. So we got to clear this from memory as well, so that it's not a problem. One thing I'm going to do here in a second is I'm actually going to see what the difference, I'm going to print out the difference in time to just show how much longer. What does it actually say the official definition of this is? Python delete. What is that officially supposed to be doing? It's an object. So they also use the delete variable lists. It says everything in Python is an object. Almost everything has attributes and methods. So the main objective of Python delete is to delete the object in the Python programming language. Here, object can be variables, lists, or parts of the list. Each object is a kind of Python object. The lease statement works by unbinding the name or moving it from the set of names known to the Python interpreter. If this variable was the last remaining reference to the object will be removed from memory. If, on the other hand, other objects still refer to this object, the object won't be deleted. I'm just assuming that they're telling me to do this because it's these are so large, and perhaps that could just cause problems with like memory issues or whatever. So I don't need to do what I said I was going to do before, just figure out the difference. This is clearly larger, and the dot product method is like 2,790 milliseconds faster. So that's a pretty sharp difference, to be honest. Yeah, I was surprised. I'm gonna run it again. I don't know like exactly what, data sets are averaging like in a real world scenario, but I imagine that it's not unusual to get up to vectors this large, and we haven't even gotten to matrices yet, so matrices are two-dimensional arrays. We haven't even gotten to those yet, so I know it's going to get pretty bonkers with compute time with those. Okay, so yeah, so this is just the vector dot product operations. And let's see if there's any extra notes I want to wrap up here with. Vectorization provides a large speed up in this example. Numpy makes better use of available data parallelism in the underlying hardware. Let me write that down here. Oops. I'm going to change this to markdown. So Numpy makes use of data parallelism using the GPU. Using the underlying hardware. I'm just going to say it like that, because it'll really just depend on the computer. But my understanding is that it's GPU. GPUs and modern CPUs implement single instruction, multiple data, pipelines allowing multiple operations to be issued in parallel. So I think if you have a like an Apple Silicon, I did look it up online. There's like an integrated GPU that they have built into their architecture, but it's like treated as one thing instead of being a separate module, or so however you verbalize that. It's not a separate thing, like a separate thing on a motherboard like you would have for like a PC or a Linux computer. But it is working like a GPU for a Mac. But there are computers apparently that have just CPUs. I think in the sense of like, if you're running like a Raspberry Pi or something like that, I don't think there's a GPU, like a dedicated GPU or anything like that. I'm trying to figure out like exactly how this relates to different hardware architecture. But I guess like the main point here to know is that like whether your computer has a GPU, even if it has a modern CPU, modern CPUs have this ability to do single instruction, multiple data pipelines, which means that things can run, operations can run in parallel to one another. And this feature is generally important. If you were to like do machine learning in the cloud, for example, you'd be using GPUs as your resource for doing machine learning instead of CPUs, by the way, which is probably why the cost of GPUs has gone up so much, aside from all the PS5 gamers out there who've been trying to get PS5s. They're probably part of the problem as well. So GPUs And modern CPUs utilize, or implement rather, single instruction, multiple data, SIDM, pipelines. Allowing multiple operations to be issued in parallel. Okay, so that's the last thing I'll put in my little notes here. Look how organized and beautiful and cute these are. Yeah. One day soon, I promise, I'm gonna put all this on GitHub. And then I'll be able to put a lovely link down in the description, and you'll be able to go check these out and use my little cheat sheets so that you can just learn this for free without having to go through and pay. Before I go, I just want to remind you that you can go check down in the description of this video to get some free links to free resources. You ain't got to go and get the Coursera course, but if you want to, I highly recommend it because it's great. It's not my course, but it is one I'm taking, and it is really nice. Other than that, there are plenty of YouTube videos. If you would like to have me add anything to this resource list, let me know. You know what I'm saying? I'll add them to that. My goal here is just to allow my learning process to be transparent. This is OpenPair, so just think of it as we're just sitting here learning together. And what else? I'll be back tomorrow at some time. I got some things to do in the tech community here in my city, but I'll be back finishing this vectorization lab up, and after I do that, then we're going to jump into multiple linear regression and get it popping in that direction and keep it pushing. So yeah, I think that is it for now. We're almost at an hour, 3 minutes shy of an hour, so I think this has been a good session. Thank you for joining me. I'll catch you on the flip side. Adios.